Welcome to this methodology unit, where I'm basically going to answer the question, which of all the different methods that are presented in this course am I to use in which situation? So for this, I prepared the overview in this slide here, which on first glance might seem relatively daunting, but let's work through this each part after another so that we can get a better idea what this is all about. So for this, first off, to better illustrate this, let me switch to this laser pointer. So the central question to start with is here in the middle. What do I want to do? And the first idea then would be, we could be asked to dissect different bundles of features. We could be asked about calculating associations between two or more variables. We could be asked in the developments in or of groups, consider different probabilities for regard with different distributions, compare two or more samples, or classify observations and variables. So that's basically three different approaches we could work through here. Well, let's start here on the left with the dissection of bundles of features, not because it's the easiest and fastest to go, but because it's the, fastest way to actually already finish one of the 6 different parts, because in this case, the only possibility or the best possibility would be a conjoint analysis. So first idea, what is this dissection of bundles of features all about? Imagine you're buying a car. The car usually considered as one unit. However, the car has different features. Color, the type of stereo, the type of interior design. And well, you're not going to consider or don't usually have a direct opinion about what is actually the color black in a car worth to you. However, if we have a retailer, they might actually be pretty interested in what is the color black value to you, what's the value of the color red, what's the value of the color blue, or in other words, what's the least valuable color to you, because then this will be the default color and you have to pay extra for all the other colors. And that's why you're going to do conjoint analysis. So you just have someone evaluate what the whole car as a bundle is worth to them. And then you use this method to get an idea what the black, or how much they value the black color, how much they value the red color, how much they value the blue color. So that's the basic idea behind conjoint analysis. So this already is the first of these 6 points. However, that's the smallest of them. So let's switch to the next part, which is here the part association. So whenever you're interested in getting the association, the strength of the relationship between, usually it's 2 variables, but it could also be more, then the first question you should ask yourself, how many observations do I have? A lot, so meaning more than 50, or only a few, so less than 50. If you only have a few observations, most of the things which require, let's say, median means in some way or another, are off the table for you. So if you only have a few observations, less than 50, some even say only less than 30. However, if you only have a few observations, then there's basically only 2 possibilities left for you. And the difference here is, do you assume some kind of causal structure or not? So causal structure, not necessarily meaning here that you test for the causal structure, but that you assume that there is some kind of causal structure. So you have an input and you have an output. If you assume something like this, a good idea would be to go with artificial neural nets, because they can learn and they can work also with only very limited information. However, or rather, let's say the advantage of artificial neural nets is also they give you a good estimate and they are independent of the scale level. So you can use artificial neural networks for nominal data, for metric data, for any kind of data. However, usually they're relatively hard to actually implement. So here, basically, this assumes you use SPSS. So we have a possibility to use artificial neural networks in SPSS, but it's a limited approach. However, it's a decent enough approach if you assume this causal structure, want to in some way model this. A different idea if you do not assume any kind of causal structure, if you do not assume any kind of structure at all, then the idea to go with would be something of a chi-squared test or something which is built on a chi-squared test, like contingency coefficients or Cramer's V. The advantage of those methods is, similar to the artificial neural networks, you do not have any kind of, aside from the nominal scale level, any kind of additional assumptions which need to be fulfilled. You do not need to have a specific distribution. The only small underlying requirements we have is that for each group, each subpart we have here, we need to have at least, well, 1 or in some cases 5 observations. But that's a relatively decent assumption. So here, this part is for few observations. You could go with chi-squared, which almost always works, or with artificial neural networks. You could also use artificial neural networks and chi-squared if you have more observations. But these are the options you're still left with if you only have a few observations. And you're talking about associations. If you have more observations, again, the first question would be assuming causal structure or not. If yes, okay, you can go with artificial neural networks, but you also have the whole area of regression analysis available to you. This is discussed in more detail in 2 slides hence. So if we have this, a lot of regression analysis approaches. So we discussed this in more detail, the different approaches, when to use which of the approaches in more detail later. So let's skip now to the no part. So what if we do not assume some kind of causal structure? So if we're only concerned with correlation or contingency. Well, then the same way with the scale levels starts again. So we start with, do we have a metric scaled variable? If yes, we can go with Pearson's correlation coefficient. If no, the next question would be, is it still ordinal? If yes, then go with Spearman's rank correlation. And if no, so if you only have a nominally scaled variable, then go again with chi-squared, Cramer's V, contingency coefficient. So that's like the fallback solution whenever you do not have enough observation, not so many observations, if you have a very limited scale level. So chi-squared works in quite a lot of situations. And well, that's also most of the parts here in this area, excluding the artificial neural networks, what is usually already discussed in pretty early statistics courses, like Introduction to Statistics, Statistics 1, or what they are called. That's basically the typical approaches of early regression or the measures of association. Which again is not so much part of an early or even in most intermediate or advanced statistics classes, is the part here if you're interested in the development in or of groups. If you go with this part, you can first ask yourself, does this have to be graphical, or can this only be focused on pure mathematics and some kind of statistical measures? If you go with, yeah, graphical dimension would be nice, good idea would be consider social network analysis. If you go with, okay, statistics suffice, question would be, are you more interested in the group dynamics, so how the group develops, how the network develops, or are you more interested in the different group members, the members in a network. If it's the group members, should also go with social network analysis. You can also consider dynamics of a network with social network analysis, but well, that's one way to go, but not necessarily. So here, an interesting idea would be to use additional meta-heuristics. They are not discussed here in detail because that's more a field which goes into the direction of mathematical optimization. However, if you're interested into networks, groups in networks, development of networks, or in general, the different associations, relations between a lot of different members of a general, let's call this network, then you can go with social network analysis. Network could be a very broad term here. Could be a group of people, could be something like geographical data, could be something like social media. So network not necessarily means people, could also be countries, regions, could be companies, could be research endeavors, could be patterns, could be scientific publications. So whenever you can relate different things to each other, you can go with social network analysis. That's why I call this development in and of groups and not necessarily networks. Okay, so this is also not necessarily one of the classical points of early statistics. However, probabilities, the part of probabilities usually is. And that's where we start here with the question, are you interested in confidence intervals or not? If you say yes, then again the question is, how many observations do we have? If you have a lot of observations, or if you have already a theoretical value for the variance or the standard deviation, you can go with the Gauss variant with the Z distribution. If you have a few observations, then you could go with the t-test variant, the t-distribution variant. In general, t-distribution variant is not so bad if you just work with sample data. So whenever you have sample data, this would also be a decent enough approach independent of the number of observations. However, if you only have a few observations, should go with the t-test variant. Okay, however, this works with few observations, but it's still a bit problematic because, well, you need to have an arithmetic mean in this context as well. You need to have a variance or standard deviation here in this context as well. So they might be slightly off if you use very few observations. So here, yeah, could be done, but again, would be better if you have some more observations as well in the t-test variant. So that's on confidence intervals. But what if you're not interested so much in confidence intervals, but in the pure probabilities of something happening? Well, then the question would be using discrete variables or non-discrete, so continuous variables. If you go with discrete variables, question would be, is there replacement taking place or not? Well, we could do the typical things, say if there is replacement, so one object can only be chosen or can be chosen more than once, then you go with the binomial distribution. If it can only be chosen at only once, you would go with the hypergeometrical distribution. So that's the classical questions you might ask with replacement. Yes, no. It could also be a different question like, do we have to consider very small probabilities? So very rare events. Then this works in the same way as with replacement, but as I said, this is more focused on the small probabilities. In this case, you would use the Poisson distribution. That's a distribution specifically focusing on rare events. That's why it's used, for example, in insurance businesses. Okay, so you're not interested in replacement first and foremost, not so much in small probabilities. You're interested in the first occurrence of an event. So not really in replacement. So replacement doesn't play any role because you just want to know what's the probability of an event occurring after 2 tries, 3 tries, 4 tries, whatsoever. So you're throwing a dice. What is the probability of you throwing the first 6 only after 10 throws at exactly the 5th throw? That's where we use the so-called geometric distribution. So that's the 4 main, let's so to speak, discrete distribution. We could add the uniform or rectangular distribution here as well. That would be, for example, the dice where all probabilities are even, are the same. However, I consider this here in the continuous version as uniform distribution. Okay, but before, if we switch from discrete to continuous, the question you should first ask you, is the probability dependent on what happened before, what happened in the past, in history? If you say no, so every decision now does not care about what happened earlier, then you're using the exponential distribution. That's also what we call the distribution without memory. That's why, because what happened before doesn't matter. So if I want to know what is the probability that my computer will crash in the next 2 hours, and I know that this probability is exponentially distributed, then doesn't matter how long the computer already was running. So here in this case I would have the exponential distribution. This also goes hand in hand, and that's where the name comes from, that the probability is exponentially increasing or decreasing. So if this is not dependent on this, it's not exponentially increasing or decreasing, then the question would be, are all probabilities identical? If yes, then well, we are back to the uniform distribution. That was what I said could also be the case in the discrete version with the dice. This could be, for example, in a continuous version, you're getting to a bus station, you have no clue when the bus arrives, but you only know every 20 minutes there will be a bus. So the question is, how long do you have to wait? Yeah, something between 0 and 20 minutes. But it's more or less the same probability for all those events happening. So that's where you use the uniform distribution. And well, in all other cases, you can use the normal distribution or can at least approximate what you have with the normal distribution. That's also an interesting feature. A lot of the different other distributions we have here can in some way, or at least to some degree, be approximated by the normal distribution. That's why it also makes sense to run, for example, a test whether one of the variables is normally distributed, but that's what we're going to talk about in the next part, in the next branch of this graph. However, first off, this concludes then also this branch here about different probabilities. And well, this is more or less what is done if you have like a second semester statistics class. If you talk about probabilities, probability theory, stuff like this. If you talk about distributions or confidence intervals. So this could be like statistics 102, statistics 2. So it's not the really descriptive part as here on the left. It's more or less a bit more advanced. It's inductive statistics. So it's a bit more advanced, but not this much advanced. A bit more advanced is usually the first tests you run. And that's many cases with comparing samples. So if we switch to this branch, the question would be, well, you compare samples, but what do you want to compare? Distributions, differences or means, or variances? If we go with distributions, so you assume that a specific variable follows a certain distribution, you can always at least if you have a metric variable, run a Kolmogorov-Smirnov test. That's not necessarily the best test to go with, but it's a test which works in most situations. For some of the distributions, there are way better tests. So if, for example, you want to know whether a variable follows a normal distribution, then I would highly recommend, for example, using the Shapiro-Wilk test, which is way better, or the results also are way better, more on point, than what you get from the Kolmogorov-Smirnov test. But this is more general. Okay, so what if the variable is not metric, if you have different classes, if you have only nominal data? Well, then the question would be, do I only have one sample? And I want to compare this sample with a given distribution? Then I could use a goodness of fit test. If I have more than one sample, like I compare two samples and want to know whether they share the same distribution, then I could go and use a homogeneity test. Usually, both of those tests are only used for classified data for different frequency tables, at least. And, well, both of those tests are actually built on a chi-square test. So you can use this for any type of scale level, but again, you're a bit limited in this. As in, yeah, you can compare this, but you only have a certain number of classes usually. You will compare. So this is not the best idea to go with if you want to do this on metric variables, metrically scaled variables. Okay, but this is like the first part on distributions. If you're interested in differences between two samples, not based on their distributions, but in general, like for example, want to know whether they have different means, then there's quite a lot of different approaches, all dependent on the scale level of what you have. And well, as there is quite a lot, similar to what we've seen with the regression part, we're going to talk about this in more detail on the next slide. However, before we get there, let's consider the part, what if you are interested in comparing variances? Well, then the first question would be, you're only interested in variance homogeneity? If yes, then use an F-test. Well, in the context of the SPSS t-test, for example, it's the Levene test. This tests on variance homogeneity. Do two samples share the same variance? This can also be used in a different context, like as a predecessor to here the part of variance analysis. However, if you're not interested in variance analysis, but just want to use the variance between and the variance inside groups to get an idea whether the groups are different, so you're working with variances, but you're not directly comparing or taking a look whether variances are the same. That's why it says only variance homogeneity, no. Then you could go here to variance analysis and just have to consider, do I have only one, two, or more than two different factors? So different variables which describe the different groups. So the classical variance analysis is the one-factor variance analysis. If I have actually two factors, so something like a contingency table, but for example for metric data, then I could use two-factor variance analysis, and if I have more than two, multi-factor variance analysis. However, this is also recaptured again when we talk here about the differences in detail. And well, that's the three parts of comparing samples with regard to distributions, to differences, means, or with regard to variances. Then the only part we are left with is with what if we want to classify our data. Again, the question would be, what about the number of observations? If we only have a few observations and we have a grouping variable, or in other words, we basically have two variables, However, few observations, you could go with correspondence analysis, because this is simply using the contingency table we up here assumed also to work for chi-squared to illustrate this in some graphical fashion. So correspondence analysis is more or less a classification, a cluster analysis analogon, which bases on a contingency table. Then one of the variables is used, for example, as for grouping, or both of them are used for grouping the corresponding observations. Well, if we don't have this grouping variable, question would be mostly interested in the graphical approach. If this is a yes, you could go with the multidimensional scaling. This could also be done without any graphical element at all, but this works really nicely on a graphical basis. Similarly, you can also do cluster analysis graphically alone, but here I just put this with a no, as in here you can also do a lot more if you actually say, I don't need the graphical representation alone. So we could also skip this part, this box here in general. This is just an idea, like a recommendation of my part. If you're specifically interested in no or yes graphical representation, use these types of methods. But as I said, both methods apply independent on whether it should be graphical or not. Okay, that's the idea. What we can do if we only have a few observations. What if we have many observations? Well, then the first question would be, do we want to validate results? So basically we already know how many groups we have. Or do we just have to determine how many groups we actually should use? So let's start with we already have some results. Then the question would be, do we have something called a grouping variable? If no, well, this is a bit of a problematic here, because, well, with confirmatory factor analysis, we don't have a grouping variable, but we already know which of our questions are summarized by which of our factors. So here we just confirm, that's also the name, what is the best way to actually build our factors. But we already know this item, this question goes into this factor. If we do not, if we have a specific grouping variable telling us this observation, this group, so if we actually go more with observations than here with variables and items, then the question would be dependent variable metric or not metric. If it's not metric, one idea would be to go with discriminants analysis. This is similar to the logit or multinomial logit we're going to see when we talk about regression analysis. If it's metric, well, then you can use variance analysis. Again, with the question, how many factors, so how many variables do I actually use more or less as dependent? We're not calling this dependent here, but just different factors. So that's basically the idea. If I already have some results, I just want to know how good are the results, or with discriminants analysis, which of the observations should go where. I want to have more or less an algorithm telling me for future data, this should go into this category. So for example, you want to have a mechanism which performs a financial rating. Tells you this should go in this group, he should get these and these credit, well, ratings, conditions. But what if we don't already have a fixed set of groups, fixed set of classes? Then the question would be, do we want to classify by cases or by observations? If we want to classify by cases, if no number of groups is set, go with hierarchical. If we already have a decent enough idea of how many groups might be usable, so we don't want to well, we don't want to validate already prefixed results, but we already have a clue how many groups might be suitable, then we could go with a partitioning cluster analysis. So how would this look like? How would this work if we assume, for example, 3 clusters, 4 clusters to be there? If we don't want to classify by cases, but by observations, by cases, by variables, then the question is, does this aim more on summarizing items into scales? Then we're again at factor analysis. So that's more or less building constructs. Or do we just want to summarize variables into groups? Then we're more or less back to cluster analysis, and the question is, do we already have a clue about how many clusters to use, or don't we? And well, that's like a first idea how to go about what we actually want to do, could do with the different methods that are available to us. So I hope this gives you a first idea on which of the different branches to use, which of the different methods here to apply to. So let's now take a closer look first here on the different possibilities to consider or test for differences, and then to the different possibilities for regression analysis. So we start with the comparisons or testing for differences. And here we have to differentiate between, first off, the different scale levels, so nominal, ordinal, and metric. And then always, how many different variables do we actually have? How many samples are we going to use? So how many groups in each case do we compare? And what kind of comparison is this? What kind of groups are they? So here we could have independent samples or independent groups, meaning one observation could be only in one of the 2 groups or more groups. So for example, if I have gender, someone could be either male or female, but he couldn't be in both groups. If you have birth city, someone could be only been born in one city, not in more than one. So that's independent samples. Dependent samples would be, I'm interviewing the same people before and after an event. So it's same people, but I have before and after. If I have more than 2 observations, 2 or more dependent samples, I could go before first event, then after first but before second event, and the third observation after second event, so the third observation. So with this in mind, we can start with a nominal scale level, 1 sample, 1 independent variable. So we have the variable and we have some given frequencies. Then we can use a binomial or a chi-square test, depending whether we only have 2 possibilities or more than 2. So that's the easy version. What if we have 2 dependent variables? Then we're going to use the McNamara test. And if we have more than 2 dependent variables, we're going to use the so-called Cochran's Q test. So the first case, McNamara, was before and after an event. Cochran's Q, different points in time, but the same interviewees. If I have 2 samples or 2 independent samples, 2 independent variables, I'm going to use either a homogeneity test, or I could also call this chi-square test, because the homogeneity test is more or less a chi-square test. And if I have 2 or more independent variables, 2 or more independent samples, then I'm using a chi-square test again, but now with different columns and more than 2 columns to compare here. So we see, whenever we talk about an independent situation, 1 variable which doesn't have to do anything with itself or more than two independent samples or variables usually works with a chi-square test. So chi-square test is actually really the fallback solution for nominal data. Only in a case when we have dependent samples or dependent variables, then we're going to use a slightly different test. So that was for nominal scale levels. So the next thing would be ordinal scale levels. So here again, we start with one sample, now with two dependent variables. So again, one observation before something, one after something. This means we here could use either the Wilcoxon or the sign test. And if we have to do this with more than two variables, we would go with the Kendall's W test. So that's the same, again, different observations in time, but with the same people, same interviews. So this was, as I said, one sample or independent variables, so the same group of people. If I have two different groups of people I want to compare, two different cities, I've done my interview in male and female interviews. So I have two independent samples. I'm going to use the Whitney-U or only U test, or in some cases Mann-Whitney test. So there's different combinations of the name. And if I have more than two samples, still independent samples, so if I have, for example, 5 different cities I want to compare, then I'm going to use the H test or the Kruskal-Wallis test. So here we see there's a structure. It's usually I have dependent groups, 2 or more than 2 observations, independent, 2 or more than 2. Or if I only have one sample, here I don't have a specific test for the ordinal scale variables, but I have something for nominal. And I also have something for metric. Here, if I know the variance, and I have like only one variable, one sample, I want to compare the mean of this sample to this test value, I could use the Gauss test. If the variance is unknown, then I could use the one sample t-test. So this depends whether I know the variance or I don't know this. And then, well, similarly continuous as with the other 2 scale levels, if I have 2 dependent samples or one sample, 2 dependent variables, I could run a 2 sample dependent t-test. If I have 2 independent samples, a 2 sample independent t-test. If I have more than 2 samples or observations, I go again for the independent, I could run a 1 factor variance analysis. If I have more than 1 factor, that was the idea as we mentioned before, I would run a multi-factor or n factor ANOVA. And finally, if I have more than 2 dependent observations, I could run an ANOVA, a variance analysis, with repeated measures, again with 1 or more factors. So there's actually quite a lot I can do with metrically scaled variables. However, for this I first need to have the metric variables. So this then summarizes most of the different comparison tests for samples we have, with the big differences, as I mentioned, depending on the scale level, nominal, ordinal, metric, and whether the samples variables are dependent or independent in nature. So this then is like the add-on on the different versions to run comparison tests, run tests for differences in samples. And we can continue with the third part, and that's on different regression approaches. Here, the first idea would be simply to run a linear regression. That's like the fallback solution here. However, if we have a problem with heteroscedasticity, then it makes sense to use robust standard errors or so-called robust regression approaches, robust estimation. This just corrects for the bias the heteroscedasticity results in the errors. So just a correction for the standard errors. So the coefficients don't change, but the t-values, the standard errors for the coefficients might change. Okay, so this is the standard version. Then the next question would be, and this could be a result, for example, of, or this could be a reason for multicollinearity. This would be if you have a moderator or mediator effect. So imagine I have just an x and a y, the x influences the y, and then I have a third variable which influences the x and the y. This would be a moderator effect. Mediator means the x influences the mediator and the y, and the mediator itself also influences the dependent, the y. So in both cases, the relation between x and y might either be too small or too large. So moderators and mediators might have an impact on the real relation between x and y. So this is something you might have to consider, might have to take into consideration when working with more complex models. A different problematic might come into play if we have autocorrelation. Well, usually if you hear autocorrelation, you're talking about serial autocorrelation. So, or in other words, temporal autocorrelation. This is mostly, however, a problem with time series data. This means that autocorrelation in general, some values of y have an impact on y, on other values in y. So in serial autocorrelation, past values influence future values. With spatial autocorrelation, this means there's like a spatial pattern which explains the development. So for example, if you go with income in different areas of a city, you have richer neighborhoods, poorer neighborhoods. So if two people, if you consider the income of two people who live relatively nearby, they will have similar income. That's just motivated by where they live. So this is like geographic effects that same and same usually go along. If you want to actually correct your models for something like these effects, you go to spatial econometric models. There, the question is, do you have this spatial effect in the dependent variables, as I just mentioned? Then you either go with spatial lag or spatial error models. If you have these spatial effects also in the independent variables, then you would use so-called Durbin models. So this was all about the general outlook of the regression equation. So let's now go to our dependent variable. At the moment, we already assumed the dependent variable, that's just as with the simple assumption with linear regression, it's a metric variable. But what if it's not metric? Well, the first idea, the easiest version, it could be binary. Could be 0, 1. Customer buys the product, customer does not buy the product. I'm happy, I'm not happy. I pass, I don't pass. If you have something like this, it's a yes, no or 0, 1 decision, you could go with logit or probit regressions. If you have a bit more than just yes, no, 0, 1, so just customer has to decide between 5 different products. So this would be still nominal data, but with more than 2 outcomes. In this case, you just use something similar. That's the so-called multinomial logit. So that's just a number of logits one after another. A bit more complex, but can imagine it like this. So that's the idea if you work with a nominal dependent variable. What if I have an ordinal variable? Well, then you can just use a so-called ordered logit or ordered probit regression. So this works relatively fine. However, you still have some requirements, because in either case, I'm assuming, at least with the ordered and with, in particular, with the metric assumption, that it's really metric. It's more or less continuous. What if this doesn't really work? So what if I only have specific values? So with Poisson or negative binomial regressions, this means what if I can only get like natural numbers at an outcome, like 0, 1, 2, 3, 4, 5, 6, 7. That's actually, as I said, the Poisson or negative binomial regression. And well, where's the difference between those two? First off, Poisson, that's if your mean equals the variance. If the variance is larger than the mean, you call this over dispersion, and that's where you should use a negative binomial model. If we also have the problem that we have a lot of zeros, more zeros than would be expected, then this usually is an idea that you have a problem with so-called zero inflation. So zero inflation models mean I first run a logit, meaning this should be 0 or not 0, and then you have a second level where it goes under the assumption that this could be 1. How does this model then look? So he basically runs logit, and then based on the logit, a Poisson or a negative binomial model. And well, going back to the Poisson negative binomial model, the main problem here is not that I have like only 0, 1, 2, 3, 4, but that I cannot get any values smaller than 0. So the whole negative part is cut off. And that's also possible in a more general version. That's what we call Tobot models or censored regression models, where a certain part of your distribution is just cut off, is not possible. So if you're just limited to one area or another, so if only positive values are possible, only values between value x and y are possible. So that would be Tobot regression. I just arranged them in a different version because the Tobot version is a bit more general than the Poisson negative binomial regression, but it's the same problem. Okay, so that's basically these approaches. Then, well, all of this is still linear. What if you have nonlinear relations? Well, then first off, I would say really consider whether it has to be nonlinear, because except for potential exponential growths or logarithmic growth, it's relatively seldom, except if you might have seasonal pattern with time series data, that you get something which is nonlinear. So it's possible to run a linear version or a very simple model. Usually go with the very simple model. However, there's quite a lot of different linear approaches, and you can run all the stuff above also with nonlinear models. Well, as I said, mentioned the term time series quite some times. So all of this is based on cross-sectional data. If I have time series data, I can use either ARIMA models, so I have an AR term, autoregressive term. So my observations today are based on my observations in the past. An MA, moving average part. So my errors now are based on my errors in the past. An integration part. So I have more or less a linear trend, quadratic trend. So some kind of trend underlying all of this. And then I could also extend the ARIMA part by an X. So I could also include additional independent variables. The difference between ARIMA models, Gauge models is more or less, Gauge is, the G stands for general, and the CH is for I don't have fixed variances in this case. So they could also vary. So it's a more general term, more general model. And that's something which in particular in finance is applied quite a lot, or more advanced models than the Anzeige, but more or less with the same structure. So that's something to go with if you work with time series. And then one step ahead would be like panel models. Panel regressions. Here, the first question would be, do I run a fixed or random effects model? That's related to an Hausmann test. So which of the two models is actually allowed? Random effects could also always be run. For fixed effects, you should run a test first. Well, then, basically, time series and panel models could all be used in conjunction with what we discussed above for normal regression models, for normal cross-sectional models. So you can run moderator analyses, you can run an ordered logit regression for panel data, you can use a panel logit regression approach. So all of this stuff is also possible for those time series or panel models. This doesn't necessarily mean that for all of those things already some implementations are available. It's just theoretically it's possible to do the same thing. One thing we haven't discussed yet, that's more or less the AR part, which can also be included into the panel regression. So if you have autocorrelation in a normal time series model, you always include this. If you include this in a panel regression, you get so-called dynamic panel models. So that's including an autoregressive effect into a panel model. Well, as I said, that's like the typical approaches used in cross-sectional time series, so longitudinal or panel data. However, all those models have one thing in common. They are more or less based on some kind of idea of a mean. So what if you give up this idea and just rebuild regression analysis around something like a median? Then you get quanti-regression models. They're way more complex, however, they are also way more flexible. Because if I can run this for medians, I can also run this for different quantiles. Meaning I can study how my regression line changes with regard to the lower 25% of my dependent for my upper 25% of my dependent. Okay, why would I do something like this? Because the big advantage is, in all of the assumptions in the upper part, I'm always assuming that my coefficients are actually fixed. They are the same for all observations. If I want to relax this assumption a little bit, want to say, well, maybe the effect is stronger for the lower quantiles and the opposite effect is true for the larger quantiles. So I can use this quanti-regression to actually get an idea in this. However, the problem with this is, well, quanti-regression as such already introduced in statistics in the late 70s. In the context of panel models in 2008. And the real problem is, well, I could run a spatial model with panel data in a quantile context. But something like this isn't really available yet, especially if I would go spatial effects, dynamic panel model in a quantum. There's nothing implemented in this version yet, and I'm pretty sure whenever you watch this video in the next 1 or 2 years, there will still not be available anything on the big scale to use in this context, because here that's relative new approaches, in particular if you work in relation to panel models. However, it's again way more flexible than the classical regression approaches. And well, with this concluding remark, we finished also the part on which different approaches with regard to regression models are there. This already concludes then, after roughly 55 minutes, this short idea on which method to use when. So I hope you still enjoyed it. You got some ideas of what to do. And if you want to know how to actually implement or use the methods described here, have a look in the corresponding course, in particular on SPSS, or take a look in the corresponding playlist. So I say goodbye and see you next time.